This video is intended as supplementary for my introductory course in statistics and also is useful as a review for students when they are in educational measurement, maybe IRT or group measurement regression courses that are second and third tier statistics courses. So we're going to start with a recap, and the recap is an issue about central tendency. We can consider the mean of a population and that it is equal to the mean of the sampling distribution of the mean. The standard error of the mean is basically the standard deviation from the population divided by the square root of n. So let's take those ideas. We'll take the normal distribution. We'll say our normal distribution has mu sub x. That is, it has a mean in a population, and it has a variance or standard deviation of x in the population. So we could sample from this distribution. We could sample x bars, take samples, get an x bar, take a sample, get another x bar, which are means of a sample, and do this over and over and over again. We can now consider this, doing it over and over again. If we could, we'd do it into infinity, and we'd have a bunch of x bars, a bunch of means of samples. And we can take those and put them into another distribution. This is the sampling distribution of the mean for that sample size and that original population value. So we can take them, we put them in the distribution. As you can see, as little x bars are in. Now we can use that sampling distribution of the mean. We now have mu of the means, which is the same as the original population mean. And now we have the standard error of means, which is shown as we talked about earlier in earlier slides. So we now have the sampling distribution of the mean and the two parameters. So we can use this, and we can use this in hypothesis testing. Instead of drawing from the original population, we're drawing from the population of sample means for that sample size. And we can look to see whether or not the mean that we drew was likely to fall in the tail of the sampling distribution of the mean. So statistical inference, we are drawing a conclusion about a population from a sample statistics. We've gotten some data, we've gotten calculate a mean, and what do we want to say about the population? There's always uncertainty. Statistics is about uncertainty and error. We're never certain. This is the premise of hypothesis testing. Is essentially we even discuss things a little bit backwards because we will discuss supporting or refuting the null hypothesis, and that the alternative is amongst the possibilities. So in statistical inference, this is what we're going to do is hypothesis testing. So let's take hypothesis testing, break it out. We have a research hypothesis. We have a statement about the variables and their relationships. We transform this statistically into a statistical hypothesis with symbols. So every research hypothesis will end up having two sets of symbolic hypotheses. The first set we call the null hypothesis, H naught, and this is always inconsistent with the research hypothesis and contains equalities. It's sort of the hypothesis of no difference, one might say. Alternative hypotheses are always consistent with the research hypothesis, and we never use equalities. We always use the inequality. So the characteristics of the null and alternative is that they're always about the parameters, not about the samples. Even though we use the samples to estimate the population, our actual statements are about the population. For every alternative hypothesis, there's a corresponding null. So for example, if our alternative were that mu1 and mu2 are not equal, then the null is that they're equal. Or if we say mu1 is not equal to 29, maybe a value that we've seen before in a population or a test score average for a group we care about, the null would be mu equals 29. So the alternative will be mu not equal to 29, and then the null will be everything else that it's not equal, that it is equal to. Characteristics further that we have these pairs. This is how one can set up these pairs so that we have mutually exclusive and exhaustive. That is, they don't overlap. Mu and the null and alternative don't overlap, and they cover all possibilities. So the null is an equal sign, the alternative will be an inequality. If we have a less than or equal to for the null, it'll be a greater than sign for the alternative, etc. The alternative hypothesis is consistent, as I've mentioned. The null is the logical opposite. It is actually tested and either rejected or retained and contains the equality sign. The alternative is never contains the equality sign, and we don't actually test the alternative. We have directional and non-directional hypotheses. If the alternative contains an inequality not equal to, it is non-directional. If it has a greater than or less than sign, we have a one-tailed test or a directional hypothesis. For example, I believe the average GPA of American college students is more than 2.7. That's my research statement. I can create hypotheses from this. The null would be that mu is less than or equal to 2.7. And my alternative related to my research question is that mu is greater than 2.7. So I'll just use this as an example just to talk about the null and alternative. Let's say in 1995 that we had a report that in Maryland, residents took 13 minutes to get to work, and a transportation official obtained this year's travel time, and it was 35 minutes, which would be nice if that were the case. He is interested in seeing if the mean travel time has changed. So we might say the historic time counts as the old parameter of 13 minutes, and we would say, well, the null would be that there's no difference and that things should still be the same, so mu equals 13. Our alternative might be that things have changed. Reasoning behind hypothesis testing, we want to know something about a population, and all we have is a sample. So we use the statistic and try and estimate something about the population. So our statistical hypothesis for the parameter of interest never really assesses directly the population, but just uses that sample as the best evidence that we can have. We compute test statistics related to the parameter of interest. If a statistic is close to the parameter, we fail to reject the null. If it's very different, we reject the null. But how do we decide if it is close enough or not? So we use distribution theory, and as we used before, if we know the distribution or have an idea of what the distribution of the sampling distributions of the means are, and the null is true, that means given that null distribution, we're likely to find average values of the means in the center of the distribution. So we can compute a test statistic, which sets the means equal to the mean specified under the null hypothesis, and we can compare that test statistic. And then we make conclusions about the research based on our hypothesis. So step one, we could consider based on the research hypothesis, we can specify the appropriate statistical hypothesis. This might be your first step in testing hypothesis. We have to basically define the null and the alternative. A strategy here I use is that to model the researcher's belief, we use the alternatives. We set that up, and then I'll set up the logical alternative, which step two, let's figure out what test we're going to use. We need to know whether you're using a one sample t or z test, independent t-test, dependent t-test, chi-square, analysis of variance, multiple regression, etc. We set our level of significance. Typically 0.05 is used often, or 0.01. These are called p-values or alpha. These values are the value that is our critical value that we're going to test against, and are set up more so based on convention than anything. So, but 0.05 is a very typical level that one might use. Sample size is the degrees of freedom. How much is of our data is free to vary. This is not always the case that we have degrees of freedom, such as in our z-tests. And then the directionality of the test. So this is step one, is basically thinking through what test we're going to use and how we're going to set up the parameter of that test. Step three, it's useful to sketch the distribution. Of course, as you get more advanced in statistics, you'll probably just open up SPSS, SAS, R, Stata, whatever your favorite statistical package is. But it's good as you get started to graph out and map out sketch the distributions of the test, shade the region of rejection, and look for the critical values, especially in an intro course. Compute the test statistic using the sample data. Well, you're going to do a calculation form. And then finally, here we're going to compare the observed test statistic to our on the sampling distribution and state the decision about the null. So we're either going to reject or retain the null hypothesis. If the sample outcome is unlikely, given the null hypothesis is true, we're going to reject the null in favor of competing theory. If the sample outcome is likely, given the null hypothesis is true, we retain or fail to reject the null. And then finally, we need to interpret the results, maybe write up some results in APA format if you're in education and psychological testing, field related. And this is probably the most important element in that we are acting as an interpreter, going from the research question through the statistical questions, answering those statistical questions with data, and then interpreting them for the reader. So the criterion for rejection for the null, well, this rejection criteria is based on how we decide what values of data are likely or unlikely given null is true. We use probability theory here, so we can think how unlikely would data have to be for me to decide the null is false. One might think of this, the null, if this null is sort of what's already known or what's already expected to exist, we're overturning something that's known. And this is what we're doing in significance testing. Criterion for rejecting the null. This criterion is called the level of significance. Already mentioned it as alpha, and it's a conditional probability. It's a statement of risk. It is set in advance by the researcher. Again, 0.05 or 0.01 are typical values. You may sometimes hear someone using a 0.1 or a 0.005, depending on their field and their conventions. In a sampling distribution, we tend to put this point on the horizontal axis, and it will define our critical value. So here's two graphical representations. For a one-tailed test, we first see the region of rejection is pointed to here as a z-critical test. Only one tail is shaded, whereas in the non-directional two-tailed test, both tails are shaded. This will impact what the actual z-critical values will be. It's also, I'll talk about this more, but in the one-tailed test, you search one of the tails, so you can search all. For example, 0.05 or 5% of that tail, you can search in one direction, whereas in the two-tailed test, you split up that 0.05 and look for 0.025 in each tail. A one-tailed test is when we have a directional hypothesis, greater than or less than. And we're interested in looking for just one of the tails for significance. And so we only really need to go find one critical value, or use one critical value. If the alternative hypothesis has a greater than, we look for a critical value at the upper tail of the null, or maybe the positive region. And if it has a less than, we look for the lower tail or the negative region. The area corresponding to the region of rejection is equal to alpha. Again, here is our one-directional test and two-tailed, one-tailed test and two-tailed test related corresponding to whether or not we have a directional or non-directional test. So a two-tailed test, when the alternative hypothesis is non-directional, we have the alternative containing the inequality sign. And we're interested in looking for significance in either end of the distribution. So we would need two critical values, so we split alpha in half. So let's go back. Now we are thinking about this distribution. This is the sampling distribution of the mean. We have mu x bar, the average of the means, and we have the sampling distribution. We have this standard error of the means. Maybe think of this as a standard deviation of how sample means are around the grand mean or the population mean. We can use this in hypothesis testing, and we can say with the null that the sample mean that we collected is going to be equal to sort of the hypothesis, or the sample mean, the estimate is going to be equal to the hypothesized population value. So this is for maybe a one sample testing. whereas the alternatives say those two things are different. But remember, we're never talking about a statistic or a sample. We're just using that sample and placing it in our hypothesis testing to represent a population value that we don't actually have. So we have the hypothesized population here. We could collect an x bar, a mean, which that second arrow represents. So we have the mu of the population, which is this down arrow, and now we have a mu of a sample we collect, or the x bar of a sample we collected. We can compare those two distributions and see how much overlap there is. If we actually had both population values, we could see that there's a true difference in the population. But remember, that second distribution is simply an estimate of our population based on a sample. So here we take those two values, again, the null and alternative. For example, we have a sample IQ, which is 105, and in the population we expect IQ to be 100. We can look in the region of rejection to see whether or not that 105 falls in the critical region of rejection. If it did, we would have a value nested in that shaded area, and if not, it would be outside. Critical decisions. So we have four possible alternatives. We can either reject or fail to reject the null hypothesis. See that along the side, across the top. There's the true state of nature of the null. That is, the null is really true or it's really false. Well, we really don't know this true state of nature, so those two are always possibilities. So what we're trying to do is really minimize our error. So in a hypothesis testing decision, we want to be able to reject the null when it is indeed false, or we want to retain the null or fail to reject when it is indeed true. So we have four possibilities. When we reject it, it's possible we made a mistake. We have a type 1 error. Or it's possible we made a correct rejection. We rejected the null correctly. Or when we fail to reject, it's possible we have a correct failure, but it's also possible we made an error, a type 2 error. Z-tests. Z-tests are going to be related to the Z distribution we've worked with previously. One sample Z-test, the purpose is we're going to use a sample mean to test a hypothesis about a known population mean in order to determine if the sample drawn belongs to the specified population or if it belongs to a different one. This is the first test, and as I said, it is related to our Z distribution. Effectively, you are going to calculate a mean, a sample mean, and you're going to say, well, is this similar to what the population is expected to be? So if the sample has been affected by some treatment, then we might expect there to be a difference in our hypothesis. We might consider this an experimental group. So if we have a research question, which would be, does new math program improve math SAT ability? We might look at math SAT scores with students. So in this example, you have obtained 36 students who were in a new program. The average of the scores were 518. If we knew that previous scores that had a normal distribution with a mean of 500 and a standard deviation of 100, we want to know, is that 518 for those 36 students significantly different, or did they outperform the previous population value? And we might look at that in this case with a 0.05 level of significance, or alpha, critical value instead of critical value. Our statistical hypothesis in this case, the null, would say there's no difference, so we'll put an equality in there. We'll say the mu is equal to the mu of the hypothesized population. The alternative says that there's a difference. Not even necessarily, in this case, a non-directional hypothesis would just say there's a difference between the data I collected and the population value, or there's a difference technically in the two population values, using the sample statistic as one of the estimates for a population value. If this were directional, we would have a greater than or less than sign in the alternative, and an equality sign that is mutually exclusive and exhaustive in null. The sampling distribution in this case, the statistics corresponding to mu, is x bar. There are three general properties here that define the sampling distribution of the mean. We've talked about these a little already. The distribution is normal. That we assume the distribution is normally distributed. That the mean of the sampling distribution of the mean is equal to the mean of the population value, and that the standard deviation of the sampling distribution, the standard error of the mean, is equal to the standard deviation of the population divided by the square root of n, our sample size. Mentioned that this is the population standard deviation of the x bars, and n is the number of observations. So in the previous example we had 36, so we would be taking the square root of 36 in the denominator. The assumptions for the z-test are that we have independence of observations, and hopefully through random sampling, and that no one is replicated twice in this case in our data. Scores in the population are normally distributed, and that the population standard deviation must be known to do as the central limit theorem allows us to overlook to some extent the assumptions of 2, or at least that's the popular convention one might use. Typically around sample sizes of 30 or greater, we tend to have a corresponding normal distribution in the sampling distribution of the mean. This doesn't mean you need 30 people in a sample, nor does it mean 30 is substantial enough. For that purposes, you would do some sort of sample size determination. It just means that as we have weird looking distributions and you start to get a sample size of around 30, that the corresponding sampling distribution of the mean would start to look normal when you are distributing the means, not the raw population values. So this is often misinterpreted as the requirement for sample size. Also, if your sample is normal to begin with, then it's going to be normal even if it's smaller than a sample size of 30. The z-statistic. The z-statistic is the difference between the mean of your sample minus the hypothesized mean divided by the standard error of the mean, or the mean of the sample divided by the mean of the population, and then the population divided by the population standard deviation divided by the square root of n. Let's take a look. Before we go through the example, we also want to set a critical value. Because our mean is normally distributed as a random variable, the linear deviation for z-statistics will have the following properties. Mean of 0 and standard deviation of 1. That should be recapped by now. Use the standard normal distribution to find the critical value of z. So some of the critical values you might want to memorize, have on hand, or just be able to look up. These are some common values. 1.645 for one-tailed test is 0.05 level. When we look at the 0.05 level, our alpha critical in a two-tailed test, we're really dividing that 0.05 by 2, searching 0.025 in each tail, which gives us a z critical value of positive and negative 1.96. And you can read the other examples if you like to. You can pause the video, write these down, or just go to your z table in the back of whatever textbook or wherever you might search it online. So in an example, to recap, we had a population value of 500. Our 36 students had a value of 518. We want to know whether this is significant at the 0.05 level. Step 1. We go through, take our research hypothesis, and we're going to construct statistical hypotheses. Remember, there will be two, the alternative and the null. The alternative says, well, the value we collected is going to be greater than 500. The null says, well, it will not be greater, it'll be equal to or less than 500. All other possibilities, mutually exclusive and exhaustive, is the null to the alternative. Step 2, we determine what type of test. Well, sort of already talked about it. We have the population standard deviation, and we have all of the other requirements for a z-test. So we're going to conduct a z-test. We know that the mean of the population is 500 as a national value, and the standard deviation is 100. We must know the population standard deviation, which is rarely known in testing. But when it is, we're permitted to do a z-test. We'll see later on when it's not, we'll do t-tests instead. So we then specified the test, alpha equals 0.05, jokingly here because I said so, but realistically, it is a convention in the field, 0.05 or 0.01, and when in doubt, be looking through the literature that you review, your research journals. If you're going to submit an article to a research journal, you should check with that journal. You should check specifically if you're in medicine, 0.05 may not be substantial or convention in the field, whereas in some journals in education and psychological testing, there may even be a push against significance testing, and you will be reporting some effect sizes, although you should be reporting those as well. So our next thing we see is that n equals 36. We're just reporting the sample size, and we know we're going to conduct a one-tailed test with a region of rejection in the upper tail. We're doing a one-directional test here. And our one-tailed test with a region of rejection, we're going to state the hypothesis again. Their alternative is greater than 500, and our null is less than 5 or equal to 500. Step 3 is sketching and labeling the critical value. Here's a sketch here of alpha, which is the region of rejection, and 1 minus alpha is the region of non-rejection, so alpha would be 0.05, and 1 minus alpha is 0.95. In this case, as we saw before for critical values, if we're one-tailed test, we're going to look at a positive 1.645 critical value for Z. So when we calculate out the Z-score, that's an observed value for Z, we're going to compare that back to this critical value. All of this is set up prior to even having done the calculation for the test. Now we're going to calculate a Z value. So we'll just use our example here, our running example. We take the value of 518 minus 500 in the numerator. We take the standard deviation of 100 divided by the square root of 36, and we get a value of 1.08. That is the observed Z value. We're going to now compare that. We're going to see whether or not our Z observed falls in the critical region. In this case, we can clearly see that a value of Z observed of 1.08 does not cross the threshold to be in a critical value, the region of rejection. It would have had to have been greater than, in this case, of a positive 1.645. This is alpha equals 0.05. We can also think about the area under the curve or beyond. If you were to look this up in the back of your test because you were very excited about this, you would see that alpha observed equaled 0.14 here. So you'd be able to compare those two as well. You'd be able to say, well, 0.14 and 0.05. 0.05 is 5%. We're still in the 14% area of the curve, which does not cross into that threshold. And that's what that would look like, 0.14 versus 0.05. Step 5, now that we know what our values are for our critical and observed values, we can say that we failed to reject the null, we retain the null. In doing so, we could then convert this back to our research question, and we would say our results do not suggest the new math program improves math's SAT scores. One might want to, in other videos, I discuss effect size and maybe further later on, but you may want to report that effect size if you are actually reporting this, especially as a non-significant result, as that may be important for future analyses and meta-analysis. One sample t-test is going to be very similar to our one sample z-test. In our one sample t-test, we do the same thing as the one sample z. We have the same scenario, but this time we know the population mean, but we do not know the population standard deviation. So for example, if the sample has been affected by some treatment, just like before, then the sample should be different than the population. So we want to compare those two. So the distinction, as I mentioned, the standard deviation is unknown, and which is typically the case. So instead we're going to use the estimate, which is the sample standard deviation instead of the population standard deviation. That's the main difference between a t-test and a z-test. Our assumptions remain the same, although this time we don't know the population standard deviation. Previously, we had a z-test. In the denominator, we had the population value. Now with the t-test, we simply use the estimated standard error of the mean instead of the actual standard error, which uses the standard deviation of the sample. So characteristics, we still have a mean of 0, but the standard deviation is going to depend on our degrees of freedom. And degrees of freedom are the number of independent things that can vary. The t-distribution is symmetrical, very similar to the normal distribution. It's a family of distributions. It's unimodal. It has a little bit lower peak and fatter tails than the normal distribution, so it implies a little bit larger critical values for t as compared to z. Here's an example. Here's the normal distribution in blue. We can see with 1 degree of freedom that the peakedness of that t is much lower than that of the normal, and the tails are much fatter. And as we get to 30 degrees of freedom, as we get toward the central limit theorem, the t starts to approach z, or the normal distribution, and then into infinity if that were possible. As sample sizes grow and grow toward the population size, the t and z would be the same. Characteristics of the t distribution continued. We said that they are the family of distributions designated by degrees of freedom. As the sample size increases, t approaches the normal distribution as mentioned previously. Another example of differences for t's and degrees of freedom. Degrees of freedom, these correspond to the number of observations that are completely free to vary. For each thing we estimate, we sort of lose 1 degree of freedom. So in the case of the one sample t test, as we use the estimate of the standard error, we are going to lose 1 degree of freedom. So we get n, our sample size, minus 1, because we estimated one thing. Finding the critical value, well, we do this under the t distribution now instead of under the z. There's an infinite number of t distributions, so we need to know our degrees of freedom. That page number is from a textbook that I have used in the past. And you can also look at lecture notes. You can just Google or go online to whatever your search engine is and find a t distribution. To use this, we need to know the degrees of freedom and the area in the tail that we're looking for. So as an exercise, we could say that if n equals 45 for a one-tailed t-test, well, degrees of freedom are going to be equal to 44. We've set alpha ourselves to 0.05. We would end up with a value of 1.684 for a one-tailed test. If n was 20, there's 20 people in our sample. Degrees of freedom are 19 for a one sample test. Alpha we set to 0.05. We can go look that up, and we would get plus or minus 2.093. Remember, there's a distinction between a one sample test and one tailed test. One sample test means we went and collected one sample and we compare it to a population value. One tailed test is simply you're looking at one tail of distribution. So as an example, the national mean for English component in the ACT might be 18.9. You want to see if it's different, then your school is different. You randomly select 25 students, you get a value of 16.1 with a standard deviation of 5.2. You could use an alpha of 0.05 and compare that 18.9 to 16.1. Step 1, well, we would take our research hypothesis. You wish to know whether performance of students at a certain high school differs. So you just want to know that it's different, not higher or lower, just different than 18.9, the population value. Step 2, we would use the alpha equals 0.05. We're doing a one sample test. We're going to use, we have n of 25, so n minus 1 is our degrees of freedom for this t-test. We have a two-tailed test because the region of rejection, it could be in either area. So we're going to take that alpha and divide it by 2, equaling 0.025 in this case. Step 3, we go look up and sketch that critical value. In this case, the critical value is plus or minus 2.0639. Again, if for any point I'm going too fast for you, pause the video, take a moment, look these things up, try them out yourself. So here's the sketched region of rejection with our critical values of plus or minus 2.0639. And in the center, we see the region of non-rejection. So if a value we collect falls in that middle, that center, the region of non-rejection, we retain the null. If it falls outside into those shaded gray regions, we're going to reject the null. We go through, we do our computation. We have value of 16.1 minus 18.9 in the numerator, which is a negative 2.8. We divide that by 1.04 in the denominator. That's our sample standard deviation divided by the square root of our sample size, n. Going with a negative 2.69. And we compare this now to the region of rejection. We can see that that negative 2.6 crosses that threshold of 2.06 in the negative end. We're going to have our value fall in the region of rejection. The observed t value fell beyond the critical value for t. So now our observed t is more extreme, so we reject the null. Let's go back to our research question. Our research question, we can answer it now in words and say something about our results suggest that the performance of students at the high school is lower than the national mean on the English component of the ACT test. This is not a final APA write-up, by the way. This is simply a way of restating your results as based on the research question. Here's just a quick example in SPSS. We have a variable, we called it x. We want to do a one sample t-test. We can go to Analyze, Compare Means, One Sample t-test. The dialog box pops up. We place our variable x into the test variable. We need to define the test value. In this case, I set the test value to be 6. That's the population value we're going to compare our sample data to. And we get some outcome. We get our sample size in this case was 10. Our mean was 5.6 with a standard deviation of 1.7. The t value that we got as an observed value is a negative 0.7. Degrees of freedom is 9. That is 10 minus 1 is 9. And significance is 0.494. That is not below 0.05. Even though this is for a two-tailed test, this is very, very large. This is a very large significance, which means we do not reject the null. We retain the null. We did not find significant results when comparing our sample mean of 5.6 to the parameter in the population of 6. Interpretations for some of our analyses when we make statistical decisions. Conditional decisions, we have that 4 alternatives. We have already discussed the true state of nature by the hypothesis test. We can reject the null or fail to reject. And in truth, the null may be true or it might be false. The 4 decisions are that we could have an error, either a type 1 or type 2 error, or we could either correctly reject or correctly fail to reject or retain the null. We use symbols as for these decisions. This will help us understand this through conditional probability. When we reject the null and it was indeed true, that is alpha. That's our 0.05 level. We set that. If we fail to reject it, we keep the null and the null was true, we've made a correct decision. Well, that's 1 minus alpha. We set this portion of our conditional probability ourselves. So really we're saying there's a 5% chance that I could be wrong. There's a 5% chance of making an error. And we accept that 5% chance. And the reason we do so is because this is a balancing game. Where we set 0.05 does impact many of our decisions. There's also the possibility that we've made a type 2 error. We'll call that beta. And then 1 minus beta is when we have rejected the null and the null is indeed false. We like this. This is what we would call and refer to as power, 1 minus beta. Example of some probabilities we could put in there, and typical probabilities that are put in there, is when we place a 0.05 in the region of rejection, we have a 0.95 in our area of where we fail to reject or retain the null. And also we like to try to get a ratio of maybe 4 to 1 for our type 2 to type 1 error. So in this case, I'm just placing the values of 0.2 and 0.8 in our null when the null is false. In truth, you don't always know what the actual probability is for when the null is false. That's just one overlapping distribution and a second. This is so that to hammer home that there are actually two distributions that we are thinking about. There's the distribution when the null is true, and there's the distribution when the null is false. So in looking at this from a distribution perspective, we have a sampling distribution. We define the conditional probabilities in terms of areas under the curve, or null, non-null, the alternative sampling distribution. So null or non-null, so we'll have two distributions. So let's just look at the null. We have alpha, type 1 error, in the region of rejection. And then we have 1 minus alpha, a correct failure to reject null, and that's the region of non-rejection. This is the distribution of what the null distribution looks like. So if things were really true, if the null was really true, this is the distribution we would be using. Null is true, 0.05, 0.95. And you can see those superimposed into the distribution. Now, let's suppose the example where the null, the mu, is less than or equal to 10, and the alternative is greater than 10. We can depict alpha and 1 minus alpha as areas under the null distribution. 10 goes into the region of rejection as the mean. Now, what about when we have beta, type 2 error? Basically, we failed to reject the null when the null is false, and we have 1 minus beta power. We have a correct rejection of the null. Well, we have a second distribution. If, in fact, the null was false, we would have this distribution. And if we set 0.05 in this case, we would have really a 0.2 chance, a 20% chance, of creating a type 2 error. That is, we would fail to reject when indeed the null is false. An 80% chance of a correct rejection of the null. We like that 80% chance. That's a good minimum target for power. You will typically see people trying to calculate out sample sizes, and when they do this, they use power, a value for power, which is typically set anywhere between 0.8, maybe on the low end, to 0.95, or maybe in the very extreme, a 0.99 power. That is your chance to find significance when it actually exists. So here is what those probabilities are in this conditional distribution. In this distribution, which is 0.2 for the region of rejection for type 2 error, and then 0.8 for power. These are overlapping each other. When we do one statistic, we're still only calculating one value, and it will help us understand this entire the entire sampling comparative distributions. So we can superimpose the non-null onto the null distribution. So we now have two overlapping distributions. Previously we said the null sampling distribution had a mean of 10. As an example, I'm just placing the value of 13 for the non-null sampling distribution to distinguish it. So we have two distributions. One, if the null were really true, we would have the null sampling distribution with a mean of 10. But if the non-null sampling distribution is true, it should have a value of 13. We're using this in our testing theory in order to say whether or not a value should fall into one or the other. And in this case, we will test the region of rejection, but we will also be concerned with our type 2 errors, the possibility that we should have rejected the null, and power. That is, what's the chance we actually had to detect difference when it existed. Statistical power I've mentioned, it is the probability of rejecting the null when the null hypothesis is false. The alternative hypothesis is usually consistent with our research question, and we want to sort of maximize our ability to find that value. A high probability of rejecting the null when it exists is nice, but we can't directly control power. We can just do things that can influence power. Some of those things are effect size. We want to maximize the effect size if possible. This is the difference between the true population and the hypothesized mean. In a raw score sense, you might think about effect size as the difference between the mean of the population and the mean of the sample you care about. Or when we go to look at two sample tests, or even an analysis of variance with multiple samples, how different are the means of the samples? Generally, if you increase the size of the effect, you will increase power. Variability. The standard deviation of the dependent variable affects power. When standard deviation is large, standard error is large, leading to less extreme values of the test statistic. So all other things being equal, lower probability of rejecting a false null hypothesis, the lower the power. So when the standard deviation is small, standard error is small, leading to more extreme values of the test statistic. So all other things being equal, higher probability of rejecting a false null hypothesis, the higher power we have. Thus, reducing any unexplained variance or variability in scores on the dependent variable leads to an increase in power. Reducing the standard deviation leads to an increase in power. The smaller our variance that we have, the more the power we will have. It shrinks, you might think about it as shrinking the distribution. Sample size is the thing we can usually impact the most. An increase in sample size leads to an increase in power. So generally, this is one of those areas where we tend to do sample size determination and say, what is the sample size that is needed for a certain power level, for a certain chance to find a difference if one should really exist. Level of significance can impact power. Be cautious as with this. You don't want to change the level of significance just to do so. In the diagram, we place the dividing line between the region of rejection and the region of non-rejection on the null sampling distribution, and we see that is the case for both distributions, also the alternative. If we increase alpha, we move the division line to the left. There will be more area on the null sampling distribution to the right of the dividing line. In general, if you increase alpha, it leads to an increase in power. But be careful, you're going to increase your chances of type 1 error. So it's not worth increasing alpha typically to increase power, and this isn't a game one should play. You should set an alpha level at 0.05 or 0.01 or the typical convention, and power will be what it is. From there, you can adjust things like sample size or try to refine your variability. You can, however, consider one versus two tail tests, as there's a payoff for one tail test and a negative. So just as we looked at with increasing or decreasing alpha, a one tail test, we would have a critical value of 1.645. For a two tail test, that critical value in the positive area would be 1.96. So this has the ability of changing power. But remember, with a one-tailed test, you're only looking in one tail. If you choose to look for in that direction, and even if something is large and the opposite magnitude, you do not consider that significance. So with a payoff, you also have a negative here. In general, though, directional hypotheses are more powerful tests. But these should be when you have a hypothesis where you're very certain that that's the direction you wish to look in. We're now going to move away from power to confidence intervals. In other classes, we've talked maybe a little bit about these. In general, we are looking at an interval instead of just a point estimate now. We can relate these back to both Z and T scores and use Z criticals and T criticals. When you have a mean, you may not even know what the population value is. So this allows us to put a sort of distribution or likelihood around an estimate. Here we can see that the calculation is the mean of a value plus or minus, so we'll really have two values in the end, the Z critical value times the standard error of that mean. We can use the z-critical values that we've seen before. So for example, if you want a 90% confidence interval, you would use the z-critical for the 5% or 0.5 in the tail of 1.645. A very typical 95% confidence interval has z-criticals of plus or minus 1.96, and a 99% confidence interval has a z-score value of 2.57. To calculate this, we need to know these three values. We need to know the mean of the sample, the z-critical value of interest, and the standard error. So we can see here we have effectively two equations, one for the positive end, one for the negative end. I say positive and negative, well, it could be both positive and negative depending on the mean and other values. This gives us an interval as opposed to just one value point estimate. So for example, if we have a mean of 100, a standard deviation of 15, n equals 100, sample size equals 100, and alpha equals 0.05, or we know a 95% confidence interval. We can plug these values in. We can take the positive and negative. We can say mean of 100 plus or minus 1.96. We know that from looking up the the z-critical values I've showed you earlier. And we're going to multiply that by 1.5. Why 1.5? Because the standard deviation is 15. Divide that by the square root of 100, which is 10. 15 divided by 10 is 1.5. That's our standard error of the mean. Be careful not to put in just the standard deviation here. So we have two equations, 100 minus and 100 plus 1.96 times 1.5. We calculate those values. So the confidence interval around the mean of 100 ranges from 97.06 to 102.94. It's important to note that we're not certain that that value is within there, that range, that interval. But what we might say is that if we were to calculate out 100 such values, that 95 out of the 100 values in a 95% confidence interval would have the true value contained somewhere within it. We can also do confidence intervals when we don't know the population values, so we can replace the z-critical with the t-critical and do the same calculations. That basically leads to a somewhat wider confidence interval. To give you some context of effect size, raw effect size might be the difference between two means. So we might have a mean of 100 and a mean of 200. The raw effect size in that case would be 100 minus 200 would be negative 100. In this case, we're going to divide by the standard deviation. Note the difference here between basically our z-ish and t-score philosophy is that we're not taking the standard error in the denominator, we're taking the standard deviation. So if you know the population value, you can use it, but if you don't, you'll use an estimate. So in this case, we could be using, in essence, very much similar to a z or t test. We can take the mean of a sample minus the population value, or eventually we'll see where you can take two different means, look at the difference divided by the standard deviation. If you don't know this population value, you use the sample. Later on in two sample t-tests, you might use a pooled value. Also, people tend to report this as a Cohen's d as a absolute value. Here I have some listed values of 0.25 as small, 0.5 as medium, and although I have 1 here as large, I think it's now sort of common convention also to consider maybe 0.8 as a large value. That is also true. Effect sizes effectively could be used for your correlations in that those sort of represent the squared correlation is a way of looking at effect size. We're now going to move hypothesis testing to independent samples, where we have two different samples, two different groups, or dependent samples, where either it's the same group with the repeated measures, or we have cause to believe there's a dependency between those samples. Research considerations for independent samples. Well, the selection of elements making up one sample is unrelated to the other. There are two ways to achieve this, and we typically can do this through random sampling into two different groups, or random assignment. Random sampling is sampling from the population at random, where random assignment is taking the data and randomly assigning them to one of the two conditions. Statistical hypotheses, well, when you conduct a hypothesis test on an independent sample, we're looking for the difference now between two populations, and we have two samples, so we're going to use the samples to estimate the population values. So here's two overlapping distributions. We can say statistically, in a non-directional sense, that mu1 minus mu2, they should be equal to 0. So the null says these two things are equal. The alternative says, no, they're different. Your research hypothesis is almost certainly likely to say the two populations are different. That is, if you have two independent samples and you apply a condition to one and not the other, you expect to find a difference. And that's what the null would look like. We can also have directional tests with greater than and less than symbols. A warning about directionality, just be careful when you follow the direction. Order matters. A negative in this case, or a positive if you have mu of 20 and mu of 10. The direction of that hypothesis matters. 20 minus 10 is a positive, whereas 10 minus 20 is a negative. So just be careful when you choose a direction. Also set up your hypothesis appropriately. So the statistic corresponding to mu1 minus mu2 is x bar 1 minus x bar 2. In the beginning of this video, way back, probably about an hour ago, we sampled from a population many times and created the sampling distribution of the mean. Well, here we have two distributions. We can think about sampling from both, sort of creating the sampling distribution of the mean through the difference of these two population values over and over and over again in the same sort of process. The sampling distribution of the mean now is around the difference between these two scores. So we expect the mean of the sampling distribution of mean to be equal to mu1 minus mu2. And then the deviation, or the standard error of the difference between the means, is also proportionate to the two values. So now the standard error of the difference is equal to the square root of the variance of population 1 divided by the sample size for that one, and associated with the population variance for sample 2 and the sample size for sample 2. Correspondingly, and what we'll end up using is the standard error of estimate, the estimate of the standard error of the difference between the means. We just simply use the variance, or the standard deviation, as we might say. Using sampling variance in place of the population values, we're basically going to be using a t-statistic instead of a z. I won't even discuss the z-statistic here because it's so infrequent, and you'll almost certainly be conducting independent t-test as opposed to an independent z-test. Should you actually have the population values for both samples, one could do an independent z-test. So the assumptions are simply extended with a little bit of difference. The scores of the dependent variable are measured independently both within and across the treatments. Scores on dependent variables are normally distributed in each theoretical population, each treatment group, and we have this concept of homogeneity of variance, that the variances for both populations for each sample are the same. From the population, they are the same. That is, variance 1 is equal to variance 2. For number 2, we still rely on the central limit theorem, and sample sizes of 30 or greater tend to be normal. We also see that sample sizes are equal. We can overcome assumption 3. That's convention, but I will say that's not always the case, and some current literature says there can be certain interaction effects. We won't go into that right now. It's a more advanced topic, but I will also say that homogeneity of variance is not a perfect thing. We don't need a variance of 2 equaling a variance of 2. We need it approximately equal, and we will see the testing of homogeneity of variance in later lecture. The t-statistic for a independent t should look very similar in the numerator to the one sample t. Instead, the denominator has changed. We have a pooled estimate of the population variance. But effectively, I use this d bar to just signify, in this case, the difference between the two means. And in the bottom, we have a standard error. That's the same for every z-test and t-test we'll do. We're basically finding in the numerator the difference between two means, and using some form of calculation to create a standard error. And that ratio creates our statistic, in this case, a t-statistic. We use a pooled estimate of the population variance in independent t-test with the assumption of homogeneity of variance, that the two sample variances are equal. We just pool the two values. Basically, it's a weighted pooling to create that pooled variance. We generate it by n minus 1, the sample size minus 1 times the variance of group 1, plus n2, the sample of group 2 minus 1 times that variance, divided by n1 plus n2 minus 2. So basically the weight of the variance for group 1, the weighted variance for group 2 divided by the total number of both groups minus 2. The estimated standard error, the difference between the means, just like we saw before when we had an estimated value. This is for a sample. The standard error is the standard deviation of the sampling distribution, and we're going to use our estimate, the best estimate that we have. In this case will be the pooled variance, because we can rely on both samples to create a better estimate. So to clarify as we go, the first thing we do in creating a standard error is create the pooled estimate. Then we take that pooled estimate, that variance squared p, that s squared p, and we place it into the calculation for the standard error. So we're going to use the pooled estimate to calculate the standard error. So in eventually conducting the standard error, step 1, we calculate out the pooled variance, which is the equation we showed before. If n's are equal, this is sort of a shortcut conceptually. We can take the variances and divide by 2. The standard error, now, in order to calculate it, we are taking the pooled variance and placing it into the equation to calculate out the estimate of the standard error. So that's the denominator of the independent samples. T is that estimated standard error, and the numerator is just the difference still between those two means. So in order to help, we're going to use an example. I will also add that the video is simply intended as support for the course. So if you've had trouble following along, you should be attending lecture, reading your text, coming to office hours, and following up where you can, even using online resources. I don't consider the videos sufficient. I consider them support for most of the classwork. So going on with this, here's a real type of example here that we can look at for reading skills. So we obtained a sample of 15 students that were taught with the whole word method and 15 with phonics. The researcher, us, we administer a test of reading fluency to all students in the study. The scores obtained by students in the two groups are shown in the table below, and I'll show you that in a second. Conduct an appropriate test at the .05 level. So here's the data that we've collected, and along with the mean and standard deviation for each group. Group 1, whole word method. Group 2, phonics. Raw score data, the means of around 9 for the group 1 and 10.5 for group 2, along with their associated standard deviations. So step 1, our research hypothesis, we think there's a difference, is going to be converted into two statistical hypotheses, the null and alternative. The null says there is that mu1, or group 1, reading group 1 equals reading group 2, and the alternative says there's a difference between them, or that the difference between group 1 and group 2 is not 0, could be greater than or less than. We now need to sort of think through what we're going to do. We have a significance level of 0.05. We have two samples. We know we're going to do a two-sample t, in this case for independent groups. Our n for each group, We have n equals 1 and n2 equal 15, but we can calculate degrees of freedom. In this case, we're estimating two things in our data, so our degrees of freedom are n minus 2, so we can take group 1 plus group 2, which is 30, minus 2, which is 28, to calculate our degrees of freedom. Sketching the distribution, we go back, we look up for our degrees of freedom. For a two-tailed test, we have a critical value of plus or minus 2.048. So if the threshold for degrees of freedom of 28, our critical value is going to be set at positive or negative 2.048. And we're going to look to see if our observed value falls in the critical region in either tail. In this case, one of the things we might want to do first, if we were calculating this by hand, is go ahead and calculate out the pooled variance. So here's our data where our sample size for each group is 15, and we have the means and standard deviation for each group. We can go ahead and plug in first the sample size for N1 and the sample size for N2. We then can plug in the variance or standard deviation, in this case, for group 1 and the standard deviation for group 2. I've color coded that to maybe make it easier for you. You can also hit pause, take a second to think about this. I'd go ahead and put those values in there. The reason I said standard deviation, even though in our equation we're using the variance, is simply the squaring this standard deviation is the variance. Make sure not to miss this step. This leads to a typical error. So we're taking 15 minus 1 for each of the samples, and then we're multiplying that by the associated squared standard deviation, dividing the whole thing effectively by the degrees of freedom. 30 minus 2, 28. We calculate that out. We end up with a value of 15.88. So we've done all that work, but that is for the pooled variance. That is not the calculation, nor is that even the full denominator. The pooled variance goes into the standard error in the denominator to calculate out the standard error. We use this just like we did before. We calculate out the standard error in the denominator of 1.45. And in the numerator, it's just the difference between two means, a negative 1.5 in this case. We come up with a test observed value of negative 1.0539. Now we locate the observed test statistic. We can compare it to our critical value. In this case, we can clearly know that 1.05, negative 1.05, did not exceed those critical values we showed you earlier. We now interpret the results. We can say that our results do not suggest there's a difference between the phonics and whole word methods. This is outcome from SPSS. We see group statistics, which are familiar. The independent sample test for this, for now, given equal means and variances that we will say are close enough to each other, we will use the score for equal variances are assumed. Our t-value is negative 0.054, degrees of freedom of 28, a significance of 0.301, a larger significance than 0.05, and we do not have significance. We will also see later on where we will use equal variance not assumed, but for now, the area circled is the t-statistic of interest. Effect size calculations we will handle more so in another video or more likely in class. But just so you know, you can use sort of the same philosophy for effect size to look at the difference between two samples as you can to look at the difference between a sample and a population value. When the variances are not assumed, we can't just pool the two variances, or we should not, I should say, pool the two variances. There's another statistical test or independent test we can use. We use the Welch-Aspin test when we assume that homogeneity of variance has been violated. That is, the variance of group 1 is different than variance of group 2 in the population. We typically say when sample sizes of the two groups are equal that we're somewhat robust. Violations are not substantial as much to impact on type 1 and type 2 error. There may be some literature of that more into now when you go into analysis of variance. We will talk more about that. When sample sizes are equal, for now, we will overlook the homogeneity of variance assumption, but when they're not equal, we will conduct the other statistical test. In truth, when you are conducting a test, we will do this in SPSS. We will look at whether or not there's a significant differences between the variances, and then you will be able to observe both t-values. But selecting the one not that fits your needs the most, but the appropriate method is to look at the variance. If the variances are considered equal, then you can use the test for equal variances. When they're not, use the test when equal variances are not assumed. Levene's test to test the equality of variances. This is conducting a statistical test to determine if the two population values are equal using the sample data. Statistical hypothesis that we will use here is for the null is that variance 1 minus variance 2 is equal to 0. That the alternative says that they are different. If Levene's test is significant, more extreme than that 0.05 level, then the homogeneity of variance assumption is not met. So we would have to use the Welch-Aspin test or equal variance not assumed in our outcome for an SPSS or SAS output. The assumptions for the Welch-Aspin test are very similar, but now we don't have to assume equality of homogeneity of variance. Here's an example of a flowchart adapted from Professor George McCready's notes that I used when I was at the University of Maryland. And here's a flowchart showing what our decision-making process might be. When the n's are equal, we're going to use the assumption of homogeneity of variance and use our typical independent t-test. When they're not, we're going to go ahead and do Levene's test, and we're going to see whether or not the assumptions are met. If the variances are not the same, then we do the Welch-Aspin. In general, for SPSS, we go ahead and can look at Levene's test either way, and I'll show you that in a moment. So we'll use this example. I'll let you read it, but it's about dieting. We're going to randomly assign two different groups to a sugar-free and low-fat diet. And we're going to conduct a test to see whether there's a difference. We take our statistical research hypothesis and build statistical hypotheses again. And now we're going to see which type of test that we're going to use. In this case, we are going to have a non-directional test. We're not sure which of the two that will be higher or lower. So we'll go through our logical process. In this case, if the n's are equal, we're going to, if they're not, we're going to check the homogeneity of variance. Then we're going to go through and, if need be, use the Welch-Aspin test. In this case, we're saying you do need to use it. So another way of looking at this is just as the output of SPSS. The first thing we look at is what is this F test. You'll learn more about that in analysis of variance, but for now, are the two variances equal? Well, that's a large F value, and that's a small significance. That significance is 0.004. It's less than 0.05. It's small, which means the equality of variance is not assumed. Those variances are not equal to each other. So instead of using that first row of data for equal variances assumed, we're going to use the second, highlighted here. We're going to use this t-value with these degrees of freedom and significance tests. We're not going to go ahead and calculate those degrees of freedoms online for the Welch-Aspin. See your textbook for that in your general introductory stats course. So continuing with our example, we have a significant Levene's test. The null hypothesis of the variance is rejected. This isn't the t-test overall. It's just the Levene's test is stage 1. We see that it is significant, which means those variances are different, which means we use the Welch-Aspin. Again, we're not computing those degrees of freedoms here in this lecture example. We could still, if we wanted to, sketch the distribution. For now, we're not going to calculate out the critical values of the Welch-Aspin test, although you could look it up, round it up in the back of your book for degrees of freedom. Compute the test statistic, and here we're going to rely on SPSS output. Here we're going to rely on the SPS output. We can see that the sample sizes were slightly different, 12 and 10. Just the means kind of popped to us, sugar-free being 5.9 almost, and low-fat being just above 2. we go down and we see that the t-value, really in either case, is significant, but it is very important to report the correct t-value here and to understand why, because there will be cases where equal variance assumed and equal variance not assumed could lead you to different results. In this case, our t-value that we're going to use is 4.085 and is significant, below the 0.05 level. Looking at those values, we will reject the null and we will be able to discuss the alternative. When we interpret, we say our results suggest that there's a statistically different in percent of overall weight loss between sugar-free and low-fat diets, especially the mean in conjunction with the test statistic. We can conclude that sugar-free diet is significantly more weight loss than low-fat diet. So if you're going on a diet and this data were accurate, and you believed in the generalizability of this data, you'd likely want to go more on a sugar-free than a low-fat diet. I don't make the claim that this is true. This data is, one, from a small sample, and two, made up. We're now going to switch gears to the dependent test. Dependent sample design. Typically, we're talking about a repeated measures design, but it's a study in which the measures in one sample are related statistically to measures in another. There are three ways that we can conceive of. First, the repeated measures design. I test a group 1, I test them again. They're the same subjects repeated over time. We could match subjects, where in a study of subjects with two samples are matched with some by the experimenter on an outside variable. Or we have matched pairs. Often you see this in like natural pairs or twin studies. The advantages are we can ensure comparability over time or between dependent groups. It reduces the number of subjects in a repeated design. We can use, allows us to manipulate time as an independent variable, and we have fewer assumptions. So we have some limitations like ordering effect with repeated measures of the same subjects. We could have exposure to the treatment can impact outcomes. For example, in an English composition example, the effect of listening to classical music continue while students were writing a second essay in silence, whereas the students who maybe started with silence would not have that effect if you reversed that order. There's also regression effects that can occur. Subjects are selected because of extreme scores, and you could end up with remeasuring and they're closer to the mean. College retention program example, a regression effect might occur if only students with low first semester college GPAs were selected. The regression to the mean effect would say they would naturally be greater just by regressing back toward the average. Our statistical hypotheses are going to surround the difference between scores. We can use the same hypotheses that are used in ideas that are used in independent samples. However, we're going to formulate them around different scores, not just around group 1 and group 2. We can sort of use the d value, x, of for person 1, their score at time 1 and time 2, as a different score. So we can see here an example going across 1 for a pair for a person 1, time 1, treatment 1 score is 6, treatment 2 score is 5. The difference is 1. You can go down the rows to sort of look at that in more detail. So the mean of the population of different scores is calculated by the mu of group 1 minus mu of group 2. And we can use this relationship in statistical hypothesis testing. So we can simply say, for the null, we expect the difference to be equal to 0. That is, the difference at time 1 and time 2, there's going to be no difference. Whereas the alternative says there will be a difference of some form. The corresponding statistic, then, we will be using is the mean of the different scores. Go ahead and hit pause and look at this, but effectively you're just calculating out different scores, and you can do all of this statistics based on the difference score distribution instead of two separate distributions. The sampling distribution is based on the mean of difference scores. So there are three general properties as before. We see that they're normally distributed for the different scores. The mean of the sampling distribution is basically the same philosophy as before, mu1 minus mu2, or mu of the different scores. We can think of this as the population of different scores. So group 1 and group 2 different scores, time 1 and time 2 different scores. They're dependent. You sample once, you sample twice, you sample infinite times, and you get sampling distribution of the mean of different scores. And that also has a standard error of the mean and an estimated standard error of the mean, just like before. In this case, we rarely ever know what the actual standard deviation of the difference scores is, so we use the estimate from the sample. The t-statistic and critical values we use the estimated variance of different scores. In this case, just like we did before, we're going to rely on the standard deviation or the variance, but in this case we can just use difference scores. So we can use the sum of squares of difference scores instead of having to do this for both sampling times. Very similar to our variance when we calculate it or in a different session. So we can replace the population value with a sample estimate, our estimated sampling standard, our estimate for the standard error of the mean of the difference scores is simply the variance of difference scores divided by n, that whole thing take the square root. So it simplifies into a t observed, which is effectively all done on the difference scores, which is the mean of difference scores divided by the standard error of the difference scores. Assumptions here. Well, we assume that different scores on the dependent variable are independent, and that the population of different scores is normally distributed. Here's an example I'll let you read if you want to pause, but essentially we have 12 pairs of identical twins, so our dependent measure is not going to be a repeated measures design, but a comparative study based on an assumption that twins are similar, and we're going to be looking for a difference in IQ based on an enriched environment. Now, as a reminder, as we take our research hypothesis and turn it into the appropriate statistical hypotheses, order matters. We start with our alternative and we say enriched minus impoverished is greater than 0. So we expect a greater IQ in the enriched, but you need to follow that forward, otherwise you will get opposite results, which would impact you finding significance. If you're doing a directional hypothesis and you find something the other direction, just think, you thought so much of the direction of your impact that you chose not to explore the other end of the distribution. So when you do find something in that direction, don't cheat and use a non-directional hypothesis. Let it be a moment to completely change what you're thinking on the field. It may have a larger impact than simply just being significant. It may totally refine the way you think about an area, in this case maybe IQ. Step 2, we're going to conduct a test. We're going to use a dependent test. In this case, when we calculate degrees of freedom, because things are dependent, we only have a sample size equivalent of 12. So in a repeated measures design, if you have 12 people over 2 times, you still only have 12 people. And in any form of dependent measure test, even with matched groups, you're only going to use the sample of size that you're going to get from your difference scores. So in this case, if you have 12 people in each group, you only have 12 as your total sample size, and 12 minus 1 in this case is your degrees of freedom. You're only going to use one estimate, the estimate from the dependent measures. We're testing at the 0.05 level. We set a t-critical value of plus 1.796, similar to what we've done before, especially with the one sample t-test. And we're going to compute the value. Be sure again that direction matters for your statistical hypothesis testing. So we can do this. See the data here. We calculate the deviation, the different scores based on enriched and impoverished, and we can sum those up. We could do a calculation here. We have an average difference score of 3.75. Now you only have one value, but remember, any dependent t-test you do is going to say, well, you believe the difference score should be 0. So is 3.75 different from 0? We do the calculation here. We take our difference score of 3.75 minus 0. We calculate the denominator of standard error, and we calculate a t observed 2.43 for this dependent test. This is enough to reject the null hypothesis, which we saw the critical value of 1.7 earlier. we can say that it is statistically significant evidence that an enriched environment results in higher IQ scores than being raised in an impoverished environment. Here's an example of output for our dependent t-test. We have our paired sample statistics, our means and standard deviations. We have correlation. These two pairs were correlated at 0.925. If that correlation equals 0, you're effectively doing an independent test. So that correlation represents a lot of the dependency. And then I've circled the t-test with degrees of freedom and significance.